Assalamualaikum and hello again. So today we'll bring you another lesson. So far we have been introducing tensors, the mathematical tools that you need to describe relativity. In general, we have the general coordinate transformations, how the tensors transform under that. Then we went to special relativity, for which we use Lorentz transformations for the change of coordinates, and we see how tensors transform under those. So today we will start discussing a little bit about physics, particularly about kinematics. In kinematics, we are talking about, just like in mechanics, we have the idea of velocities and also acceleration to be described in the context of special relativity. So remember, in the case of mechanics, essentially for free particles, they will trace out straight lines. This is the same in the case of special relativity. And when there's a particular acceleration, then it will actually trace out a curve which is no longer straight. In the same way, in special relativity, we also have the particle tracing out a curve in space and time. So let's look at this particular diagram. So here's a description of a particle. So the particle traces out this curve in space and time. So the horizontal axis is essentially the space. So this essentially is condensed to one-dimensional here. And then for the vertical axis is the time. Okay. So in other words, this curve is really in 3+1 space-time. But essentially, this curve is just a one-dimensional object. So in other words, if we look at the points on the curve, okay, the points on the curve are given this coordinates x mu, but that x mu is going to be dependent on the intrinsic parameter of the curve, which we label as lambda. Okay? So this particular curve traced out by a particle is called the whirl line. Okay? So this is a whirl line of a particle. So we want to be able to describe, besides the position, we would like to describe velocity, for example. In the case of Newtonian mechanics, we know that the tangent to the curve should give you the velocity. So similarly here, we should be able to do the same. The only difference will be the velocity may have a fourth component. So we try to do this. So we consider the curve together with a tangent vector. So how do you get a tangent vector? Is simply just drawing a tangent to each point. So, and each point is given by a particular lambda. Okay, so that lambda will actually tells you how to form the coordinates. Okay, so in other words, dx mu d lambda will actually be the tangent vector. Okay, and this tangent vector essentially will give you the velocity. And for massive particles, okay, particles with mass, this tangent vector should be time-like. And you remember in the case of, so let me draw something here using the highlighter. So you have this called space and time, just like in this diagram. But if you have the unit c equals to 1, you will also have these diagonal lines traced out by photons. Okay. So that's not quite straight, but never mind. So we have these diagonal lines 45 degrees to those axes, okay, will form the whirl lines of photons. So remember, the limiting speed in some sense in relativity is given by the speed of light. So any other particles will have a much steeper slope. The slope is not the velocity in this particular case, because we have the axis to be on the time axis, the vertical axis, instead of the instead of the horizontal. Okay, so the inverse slope is essentially the velocity. So in other words, the inverse slope should be steeper for the case of those particles propagating with speed less than the speed of light. Okay, and this is essentially what we call timeline. Okay. Now, one of the properties of timeline vectors is that when you do an inner product using the metric tensor, for example, okay, so here's an inner product, the answer should be a negative number. For photons, we know that it's going to be 0. So let's try to see what it is. So we just simply expand the dummy indices. Okay, so remember that the dummy index will run from 1 to 4 in this particular case, and essentially the first 3 will give you the differential, the derivative of the position, the space position with respect to the intrinsic parameter, and then you have multiplied with the same thing. Okay, remember that eta mu nu is diagonal, so you get square here minus, okay, remember that the eta for 4 is a minus sign, so you have the fourth component, the derivative of that with respect to the intrinsic parameter. So you get a squared minus c squared. Now, we don't really know what this intrinsic parameter is, but one could actually simply do a chain rule to convert this derivative into the derivative with respect to time. So what you do, essentially, you multiply with dt d lambda. So dt d lambda will appear here, squared, dt d lambda will also appear here on the other derivative, again square. So you have this common derivative outside. So why do we do that? Essentially, now this is something that we actually know. This is essentially the derivative of the position with respect to time, which is just simply the components of the velocities. Okay, so you have vi squared corresponding to the dxi dt squared, and then dx4 x4 is simply ct. Okay, so when you differentiate with respect to time, you get your c. So in other words, you have c squared. Now, the addition of the component squared will actually give you the magnitude, v squared. And then over here you have c squared. Since we know that v squared has to be less than c squared, so in other words, this quantity should be negative, because this is a square and this term is a difference of squares. So this will be negative times something positive, so you get negative quantity. And that verifies our mentioned fact earlier, that the tangent vector should be a time-like vector, which in this case will give you quantity less than 0, negative. Now let's do another thing here. Consider the case of two neighboring events, one coordinatized by x mu and the other is coordinatized by x mu plus dx mu. So one could actually form the interval ds squared, the 4-dimensional interval, using this eta mu nu dx mu dx nu. But now what we could do is simply made the derivative of this differential with respect to t, okay, and then you have a dt squared here, but then what one has is this particular thing, okay, and that quantity is just almost the same thing with this quantity. The only difference there is only the variable that appears at the denominator. But essentially, you can use that and this answer to substitute inside here. So in other words, you will have v squared minus c squared times dt, and then you have dt here. So in other words, dt is just simply 1. So in other words, what we have is essentially v squared minus c squared dt squared. So in other words, essentially your ds squared is a negative number, as it should. Okay. But what can be done with this? Essentially, you can manipulate this relation to define a positive number. Okay, so you just swap the terms around, and basically this gives you a negative ds squared. Okay, take the square root of that, divide it by c, so that you get a temporal quantity, and call it d tau. D tau will be defined as the proper time. Okay, so we will get to that in a minute. But essentially, you can see that d tau is simply 1 over gamma dt by just doing the manipulation here. Okay, remember that ds squared is something that we already know. Okay, ds squared is essentially that. So you get let's go to the next page. And the fact that ds squared is scalar, d tau will also be a scalar. So in other words, d tau will not change under Lorentz transformation. And this is convenient. And remember that d tau is a temporal quantity, just like time. And this particular temporal quantity doesn't change with Lorentz transformation. So it's a convenient parameter for us to use in to define vectors, for example. So what we want to do is remember that we had the tangent vector as dx mu d lambda. So instead of using dx mu d lambda, we'll have dx mu d tau instead. Okay. So if you look back, what is dx mu d tau? Okay, let's consider a particular case where you go to a particular frame for which the particle is momentarily at rest. This is called the instantaneous rest frame or proper frame or co-moving frame. So at that particular point, so if you think of what happens there, here you should have dx I dash dt or d tau. Remember, tau is just a temporal quantity. So this like it essentially gives you like components of the velocity, and then dx4 dash dt will just give you the constant c. But for the instantaneous rest frame, this will tell you that okay, the velocity here is essentially 0. Okay. So if you really think what this is, so you can think of frame attached to the particle itself. So the particle will see itself as having 0 velocity. Okay, so that's why it's called co-moving frame. And so if you see in this particular case, in the proper frame, so you get ds squared equals to minus c squared dt squared, since v is essentially equals 0. So in other words, one can see that the tau is just like uh, the moving frame's time coordinate. So we can interpret the tau as the time registered by a clock co-moving with the particle. Okay. So if you really want to know what would be the interval, time interval for particle moving from event A to event B, now this would be actually depending on the frame, but if we take the frame of the particle itself, then this will be just the integral of the tau from the point, say, A to B. And this you can easily get it to be equals to 1 over gamma dt, okay, by using chain rule again, and essentially give you square root of 1 minus v squared on c squared integrated with respect to t. And this is essentially what we call the proper time from event A to event B. So you can make it as a function. So you fix a particular point A, just like you fix a point on a curve that gives you the origin. So you can fix this point and then let this t, okay, will be a variable. And essentially what you have is you have a proper time expressed as a function of the coordinate time. So now we are ready to actually define the idea of velocities. So our idea essentially is just like the tangent vector case. So we have dx mu d lambda. So now instead of d lambda, we use the proper time that we have mentioned earlier. And tau in that particular case is indeed a scalar. Okay. So this is defined as the velocity for vector or the for velocity. And we can see that essentially this for velocity will indeed transform as a vector. So you just simply look at say the dash coordinates, the velocity vector in the dash coordinates, it will be given like such, and you have d tau dash, but d tau dash, since it's scalar, is just the same as d tau. Then in other words, the factor that remains changed under the coordinate change will be the one on the numerator, and that gives you the Lorentz matrix. Okay, thus you can actually see from here it transforms like a for vector. We can actually see what this for vector is, okay, again by using chain rule. So you re-express the derivative in terms of time, okay, the coordinate time instead of the proper time. So what you have here, you just have the ddt of x and ddt of ct. So in other words, you have v for the spatial components and time, and then the fourth component bc. But remember, over here we have the relativistic factor that comes out from this factor. Okay. So now if you try to take the magnitude square of this for vector, you see that you really get a Lorentz invariant. So you just use this answer that we had earlier. So you get gamma squared, v squared, and then you minus c squared. So you get that. So what's gamma squared? Gamma squared is 1 over 1 minus v squared on c squared. And then on the numerator is just the one in the bracket. And then you can rearrange this, and then you get your answer to be minus c squared. Alternatively, one can just use the definition itself, and then you'll find that you have eta mu nu dx nu here. That gives you a ds squared, and then at the denominator you have the d tau squared, and then you just simply give the definition of d tau squared, which is that, and then you get the answer to be minus c squared. So in other words, you can immediately see that, okay, it's a convenient thing for velocity in relativity, for any four velocity for that matter, it should give you this invariant of minus c squared. Okay. Now we can proceed now again to do acceleration. So for the acceleration, essentially just take the four vector of the velocity dv mu and take the differentiation with respect to tau, and that we define as a mu, which is what we call the forward acceleration. And we can see what are their components just the same way. You convert it into the time coordinate, and essentially what we have is essentially the derivative with respect to time of gamma v as the first three components, and the time derivative of gamma c. Now, in the proper frame, one can show that v equals 0. One can assume that v equals 0, okay, as by definition. So you can see in that proper frame, your gamma is actually a constant. Okay. Indeed, if you take the derivative of gamma in general, okay, so in general, this is no longer 1. Okay, so you need to consider the fact that v is probably changing with respect to time. But what's going to happen if you do the algebra manipulation right, you'll be able to show that this is essentially equals to 0 this equals 0 if v equals 0. Sorry about that. Okay. So in other words, d gamma dt in the proper frame is actually equals 0. So in other words, in the proper frame, one will be able to write down what the components are. Essentially, the partial component is just dv dt, which is just your normal acceleration. And in the fourth component is actually 0, the fact that we use v equals 0 in the proper frame. So in other words, I'm correcting myself just now that this could be changing if there is an acceleration where d gamma dt might no longer be 0, okay, because of dv dt will be some change value. Okay. But if v is actually constant, you can still get 0. Okay. But if, say, it's accelerating, then you can see that it gives you a non-zero value. Well, the point here is, okay, this is only true in the proper frame. Okay. But what's true for all frame is the following. If you take the square magnitude, you take the inner product of the four vector with itself, then you have the fact that this is a scalar, but you can still use the one from the proper frame. Okay, you can use a0 dot with a0, and that gives you a squared, which is a positive. So, and this has to be true in all frames since this is a scalar. So in other words, what we have proven here is a mu, the forward acceleration, is a space-like vector. And remember that the velocity itself is a time-like vector, and the acceleration here is a space-like vector, that should tell us about the properties of A mu with respect to V mu. Okay, so if we just go to the proper frame itself, so you have the A mu given by this, and then V mu, okay, in the proper frame, you have zero velocity here, and then you have minus C there. Okay, so you can just simply do the dot product, okay, with a negative sign for the fourth component, okay, and that gives you again 0. Okay, but one can make this more general by just going back to the definition. Okay, so now we use the definition of A mu. Okay, now there's a contraction with the inverse metric. Sorry, here in the case is the metric itself. So what we can do is that, okay, we can see that this is a total derivative of this object minus here, if you look at this is the derivative of one of v's, but it's not on the derivative of this v. So you minus the component of the derivative on this v, but not on this v. Okay, so it's just doing the product rule. But now what happens over here, the total derivative is now taking the scalar, which has the value minus c squared. So in other words, d tau of minus c squared is just 0. And then this one is just the same version of this. Okay, it's just you can just use the index manipulation. Okay, the fact that your metric is actually symmetric, one can actually show that A mu V mu is going to be equal to 0. Okay, so I'm not doing the algebras here, but you can show this. Essentially what happens is that A mu V mu equals to minus A mu V mu. So you can bring this on the other side, and you get 2A mu V mu equals 0. Now in general we might have two four velocities, say u and v, say given by this small u and small v for the three-dimensional velocities, and then you have the fourth component u4 and v4. And let's consider the case of one of them being inside the proper frame. So in this case, u mu equals 0c. And what happens in this particular case is that you get the answer to be the contraction between u and v, sorry, will give you a scalar which is given by c squared gamma, and this gamma has to be the gamma that is defined by the relative velocity of the frames given by these two, the frames of one of the frame of this rest frame with the frame coming from this, which is moving. Okay, so let me go to the next page so that you can see what I mean. Okay, so gamma is a relativistic factor using the relative velocity of the two particles. So essentially this is the relativistic factor that one actually uses. Okay. And suppose that, okay, now we know that, okay, in this particular case, V mu let me go back to the picture. So essentially we have this u mu in the rest frame, okay, and then V mu will be some other frame which is moving relative to the rest frame of U. How can we actually describe this in much more detail is, let's consider this U tilde mu. U tilde mu here essentially is a 4 vector which is orthogonal to U mu. Okay, so you remember that this is supposed to be the U mu earlier is supposed to be 0C, and then you take the dot product, the inner product with U tilde mu, you'll find that this is going to be 0. So here's 0. Okay. So what are we doing here? Essentially, we are now breaking up this V mu into two parts. Okay. One part is orthogonal to U mu, and the other part is parallel to U mu. Okay. So now we can generalize the situation so that you don't need to consider U mu in the rest frame anymore. So essentially, what's going to happen is that you can now actually show using this expression that for which you have already decomposed it into a component which is orthogonal to U mu and a component which is parallel to U mu. Okay. So once you substitute this into the inner product that we had earlier, okay, U mu V mu, then you'll be able to show that it gives you the same invariant quantity. Okay, remember initially we did this for the case of where we had U mu. In the case we had U mu earlier, supposed to look here. Over here, the inner product we had here is the one with the case where U mu is in the rest frame. Okay, and we get this answer from that assumption. But now, when we go to the generalized case, okay, where you don't need to assume U mu to be equals 0 in the spatial components, but we have made such a way that V mu now be broken down into this parallel and perpendicular components. Then you'll be able to check that you get the same quantity again. Okay, and this is quite convenient. So if you need to do analysis in the proper frame, you can do it easily, but you can also generalize it when you go to other frames. Here, let's consider an example. Here's the example of a particle accelerating along the x-axis with coordinates of the following. Okay, so here the fact that it's a function of tau shows that it's not actually moving a constant velocity, and in fact is a curve, which is the hyperbolic cosine curve. And then for the rest, you let it be 0. Okay, so it's just accelerating in the x direction, and of course we should also have the fourth component, the time, should be also a function of tau. And we can check that this is okay. Remember that you need to have your ds squared equals to constant. Okay, but the constant is in fact this hyperbola. Okay. So in that particular case, if you want, you can reparameterize this hyperbola using the time coordinate. Okay, so basically the time coordinate will be a function of x in this particular case. Let's do the forward velocity. So you take the derivative with respect to the proper time. So you know how to differentiate hyperbolic cosine function and hyperbolic sine function. So it gives you that. And we can check now u mu is just minus c squared, as we mentioned earlier. And then we can also check the fact that the components for the tree velocity, in this case it's supposed to be this, okay, we add 0 0 because y is 0 and z is 0. It's just there's no function of tau over there. So you can check that Vx is actually less than C. Okay, this is a property of the hyperbolic tangent. And further, we can actually do the forward acceleration by just taking the derivative of the forward velocity with respect to the proper time. And again, we can check that, this gives you a constant a squared. So a squared is a parameter, one free parameter that appears in the curve of the hyperbola. So that's it for today. So I'll stop there for now.